Okay. Today is one of my favorite days. We get to do integration by parts.
Yeah.
Okay. So another integration technique, and this is a big deal for your BC test. Okay. So what I want you to think about, suppose we have a region bounded by x equals 0, x equals pi over 2, cosine of x, and we want to rotate it about the y-axis. I want you to set up how to do that.
Okay, wait, the y-axis. So long.
What method are you going to have to use? Shell. We're going to have to use the shell method.
Yay.
Is this bounded by the
X equals 0. Yeah, we're going to have to, well,
even there's two vertical lines in front.
so yes,
First quad.
quadrant. We have this, basically. Whoops, nope, that's fine. Sorry. We have this. And so when we rotate it, we're going to get something like this, right? Okay, we set this up. How? Andrew,
2 pi to the integral from 0 to pi over 2 x cosine of x equals.
I did not understand you.
X cosine of x. No, yeah, you're right.
Agreed?
Thanks, Graham. Yeah. Probably this first.
How do we integrate it?
Math. 9.
Math 9. Okay. Without a calculator.
Parts. Ask a friend who has a calculator.
Okay. Integration by parts is a technique that we're going to have to use. Okay? So, basically, we have a product here where U substitution is not going to work. Right? So, first of all, we're going to discover the rule for integration by parts. Okay? So I have a product here. Sorry. I want to take the derivative of this with respect to x. What's the derivative of y with respect to x? Thank you. How about u times v? What is that product with respect to x?
du dx d plus dv dx u.
Doesn't matter what order.
I know, but it's like the u's and v's. They just
Pretty annoying nowadays.
Okay. So are you okay with me writing dy equals u dv plus v du?
Yes.
Okay? Right? So we're going to integrate both sides.
Oh.
Okay? But that really doesn't make sense how I made it look, right? So this is me integrating both sides. Okay? Now I would like to rearrange this. Okay? So I am going to leave UDV and I'm going to subtract the integral of VDU. But, ladies and gentlemen, what is the integral of dy? Why? And what was y to begin with?
U times B.
U times v. So I'm gonna reflexive property.
Transitive.
No, but we just flip sides.
Yeah, oh.
Reflective. The integral of UdV is y minus the integral of v du.
There you just did both. Yeah. You did the reflexive one where you flipped them, but then you did the transitive where you substituted whatever.
Well, I really did the substitution. But yes, thank you. Here, my friends, is integration by parts. Okay? So, what we have to do is this is what we're going to start with here. And we're going to have to identify a u and a dv from our integral. Okay? Now look at what we have. We have a u and a du. Okay? So, whatever we pick for u,
That's not the derivative.
we will have to differentiate to get the du. Okay? Whatever we pick for dv, well, I see here that I have v's, so we're going to have to be able to integrate whatever dv is.
So basically pick the ones that would be annoying to integrate for your U's, and then get these to integrate for your V's. Or DV stuff.
Well, let's go back to this. Because in my opinion, these are both equally easy to integrate and differentiate. Right? Okay. I will tell you, polynomials will oftentimes be your best u. Okay? So we can let u be x, which means dv would have to be what? dx. No question mark. Yes, we would do that dx. Okay? So this would mean du is what?
One.
And v would be
Plus C.
Okay, we'll worry about this plus c later.
No.
Okay. Is that okay?
Sure.
Okay. So the integral of x cosine of x dx would be u times v. Minus the integral v du. And what is that? And now we'll worry about our plus c. We know the plus c is going to have to be there, so we'll just worry about it at the end. Okay? And there's our integral. Or our antiderivative, I should say.
Hooray. Yeah.
What?
B plus Cx is the plus C is either sine x. I know. So it'd be the integral of sine x plus C dx.
Mm-mm.
Yeah. of x plus c, so then you have the integral of plus c dx.
Well,
Actually, I guess it'd be like sine x dx plus c dx. Technically.
okay, go back to here though.
Yeah. Yeah.
Where are you getting all of this
So
plus
when you
c?
From when you did the,
antiderivative of cosine.
yeah, when you did the integral of dv, you get v equals sine x. And we said we should have the c. So wouldn't it be like the integral of sine of x plus c dx?
No, just okay.
Did you just forget about it?
We're not forgetting about it, okay? Because if we had that plus c in here, we wouldn't get back to our same product, u times v. If we had a plus c in here with one of our v's,
Sure you would. Because then it'd be sine x plus c, so it'd be sine x times plus cx.
okay,
So
you do this for me. That's what you want, right?
Yes.
Take the derivative of that right now. Take it. Hmm. Is that plus c supposed to be there?
No.
Plus C can come in, I think, whatever you want, because it's just some constant that goes into the integral.
Right, well, but yeah, but in this case, you have the end of integration twice.
Okay.
Okay, I'll just.
I don't know if you really want to count this as integration as opposed to just like
No.
the antiderivative. Like what we're doing is we're following this pattern right here.
Okay.
Okay? When we follow this pattern right here, first of all, we know taking the derivative is going to get us back to here, right? So following this pattern, we don't need the plus c until the end.
Okay. So calculus now. Sure. Witchcraft.
This
I'm trying to convince you, and
I think witchcraft is convincing.
Yeah, that's the most different thing I can get.
let's try another example. So, okay, what would be the best thing for you? And dv? Which would make du and dv, excuse me, v. Okay. Basically, okay, I have a much better, this is all coming together for me to say to you. Okay, the whole point of doing this is because our original y is u times v. So we have to identify a dv so we can figure out what our original v is. Does that make sense?
So could our dv have like a constant? Could our dv have a constant? So then like when you, I don't know. Let's go on. Let's go.
Okay. So there's no plus c, it's just x e to the x. Okay, so now x times e to the x dx is going to be u times v minus the integral of 1 e to the x times 1 dx, right? Which is what?
Oh wow, brilliant.
Okay, now what did Graham just do?
He backed up EDX as well.
E to the x times equals x minus 1 plus c over e to the x.
Sure.
I like it.
You do the 2x?
Okay.
E to the x.
True. But is that really fancy forms?
Is it really helpful? The only
I like
This would be, it would be helpful to do this if I asked you to evaluate it from 1 to 3, right?
Yeah.
That's probably when it would be the most helpful. We're not having to set this equal to 0, so. This is a very important example. Please be sure to write it down. Okay? Have we ever taken the antiderivative of the natural log? And some of you may have been wondering, well, how do I take the antiderivative of a natural log? What is it? What is it? Okay. What's u and what's dv?
dx.
No. Use the limit. Or walking out the road.
Is that what you're saying?
Yep.
Okay. Which would make du and v
1.
X.
Yeah. 1x.
So the integral of the natural log of x dx would be u times v minus integral of what goes inside the integral?
1. Yes.
How do you get that?
EDU.
v du, and v du is just
Yes.
dx. So we have x natural log of x minus x.
Plus.
Let's see, I wrote it down. Are you ready for your mind to be blown?
No, hold on.
It is
Give us some
Friday,
thought.
so I don't.
Are we gonna do some tricky stuff with the natural log like we did earlier?
Yeah, good.
Ready?
Okay,
Alright.
so let's look at this example. What would be u?
X
Ready?
dv? Okay, you want to pick the easiest thing to integrate here. Alright. Alright, so now this is gonna equal, oh, sorry. What's u? And v?
Yes.
Okay, so this is u, no, yes,
Yes. U
Times v.
why did I was second guessing myself, minus integral of
VDU.
E to the x times.
e to the x times, I'm going to put the 2 out here, is that okay?
Oh, yeah, that works.
And that's
And
one
then
we
we
already
already
did,
had-
so it's x minus.
Okay, so let's say we hadn't already done that. What are we going to have to do?
More
More integration by
We're going to have to do integration by parts again.
Wow. Say this is.
Okay, so imagine if that was like an x to the 4th.
Oh.
We would have to do it how many times? Okay. But is there going to be some sort of pattern here?
Yeah.
Probably.
Yes.
Uh-oh.
Right? We're going to subtract this, and then we're going to do the integration by parts and have another subtraction. Or that we have to do integration by parts and blah, 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 blah. Okay.
Same thing times whatever.
A table when possible, will make integration by parts more efficient. Okay? So, what did we identify as our U?
Yeah.
Because that was a nice one to take the derivative of. And dv was e to the x. And we integrated that to get our v, correct? So what we can do is we can put these into columns. What does that d stand for?
Derivative.
I'm going to take the derivative. And what does the I stand for?
Integral.
I'm going to take the integral. Okay? So what we are going to do, when you have this table set up, whatever you put in your D column, you're going to take a derivative until you get 0. Okay. Over here, we're going to have to take the integral that many times.
This doesn't sound good.
Okay. Now remember how we subtract v du in our integration by parts? So we're going to have to account for that by changing the sign here. These are going to alternate signs. There's our multiplication. So our antiderivative is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Okay, that way you don't have, technically we did integration by parts multiple times. We did integration by parts twice, but we just did it all together so that we wouldn't have to re-identify u and dv because they were going to be similar every time. Yes, Grant?
So the numbers you put at the top are just U and V.
U and dv. So this was u, and this was dv.
And then it will become v, dv again, becomes
Okay, another one? No, yeah.
Sure, let's go for it.
Although I'm going to change this to an x to the 4th.
Fun.
Okay. And when really is the chart going to be our option?
Well, when we
Okay.
have like x to the 4.
Okay, when we have x to a power, right?
Yeah.
Because we need this to go down to 0. And the only way we're going to get that done is if we have x to a whole number.
You were so close.
All right, so what is our u and our dv? Okay, so our that column. X to the 4th, then what? Okay. What else do we need? Our integration column. Please be careful.
Yeah.
So your sine of x.
Sine of x.
Sine of x.
Cosine
Sine of x. Negative cosine.
Then we match these
Imaginary number.
diagonally. Your 0 should not be paired up with anything.
Can you put it paired up with the sine x at the top?
Yes.
If that makes you feel better. So what do we have? I'm going to have to. This equals negative x to the fourth cosine of x plus 4x cubed sine of x plus 12x squared cosine of x minus 24x sine of x.
That's so cool.
Look at all that work we did.
We just saved ourselves an entire piece of paper right there.
Or a couple joules of energy on our calculator.
And in our elbows.
Are we gonna have to evaluate this?
There'll be a couple problems on your homework. I don't think I gave you any today where you're evaluating. Let's just get this
We just
down.
evaluate them all in zero?
No. No,
Wait,
no,
why this one
no,
takes
it's
squared
negative 24
Zero.
plus whatever this is.
Here's your homework.
Oh boy.
Oh boy. So it's like 1 through 6, like the first part, and then 11 through 18, the second part?
Well, I think 1 through 6 is to just identify, like the U and the DB. I think I can.
That's not bad.
I did not give you very many problems for you. Everyone say bye, Anna and Marianne.
Man.
I'll see you
How are we doing with this?